Cell 1. In this cell, we're diving into a comprehensive example aimed at predicting tourism demand across several major cities through a multi-model forecasting approach. This is crucial as accurately anticipating visitor arrivals can help businesses and urban planners better manage resources and improve the overall travel experience. We're focusing on key variables, notably the number of visitors, measured monthly for cities like New York, London, Paris, Tokyo, and Dubai. This approach to forecasting can be adapted for weekly or even daily periods, enhancing its flexibility. The intention here is to harness several forecasting methods, starting with a seasonal naive model, which serves as our baseline. We then move to more sophisticated techniques, including SARIMA, which accounts for seasonal trends in historical data. Next, we introduce Facebook's Profit, a powerful tool designed to accommodate trends and seasonal effects, even incorporating holiday adjustments. Additionally, we'll explore XGBoost, a highly efficient machine learning model that utilizes lag and rolling features to refine our predictions. Finally, by implementing an ensemble method, we can combine the strengths of these individual models into a single, more robust forecast. This ensemble will weigh each model based on its validation performance, striving for accuracy and reliability. As we navigate through this process, it is essential to keep in mind assumptions about the continuity of trends and the accuracy of historical data, as these factors can significantly affect our predictions. Pitfalls may include overfitting, particularly with machine learning models, which is something to be vigilant about. With this foundational understanding in place, the next cell will likely build on these models, exploring how we can effectively evaluate their performance and select the best approach based on real-world data.
Cell 2. In this cell, we're delving into the exciting world of forecasting
by applying multiple modeling paradigms to a single demand time series dataset. The importance of this approach lies in its ability to improve our predictions by leveraging the strengths of different modeling techniques, which can lead to more accurate and reliable forecasts. Here, we have a variety of models lined up. First up is the seasonal naive model, which serves as a heuristic baseline to establish a simple yet effective starting point for our predictions. This model uses past observations to predict future values, specifically assuming that future demand will mirror historical patterns. Following this, we have SARIMA, a well-regarded statistical time series model that captures both seasonality and trends in the data. It's worth noting that while SARIMA is powerful, it requires careful parameter tuning to avoid common pitfalls like overfitting. Next, we turn to Profit, a model developed by Facebook that uses structural and decomposed time series techniques. This model excels in handling seasonal effects and holiday effects, which can be crucial for demand forecasting in certain industries. Then, we introduce XGBoost, a machine learning regression model known for its high performance and efficiency. XGBoost handles nonlinearity well and can improve accuracy substantially, though it also introduces complexity, especially in terms of feature engineering and model interpretation. Finally, we'll explore an ensemble approach, which combines predictions from all the individual models through a weighted combination. This method capitalizes on the strengths of each model, potentially leading to more robust outcomes. As we proceed, keep in mind that the choice of models and the weights assigned can significantly influence our final predictions. With this rich tapestry of models ready for analysis, the next cell will likely take us into the realm of comparing these techniques in terms of their performance. We'll evaluate how well each model forecasts the demand, providing insights that can guide decision-making and future analyses. Cell 3. In this cell, we're generating a synthetic dataset focused on tourism demand across multiple cities, which serves as an essential stepping stone for our analysis and modeling efforts. By creating this dataset, we can better understand the trends and seasonal patterns in tourism, while also preparing ourselves for later stages where actual forecasting techniques will be employed. The function we're using, Make Synthetic Tourism Data, is thoughtfully designed to generate data over a specified time frame, allowing us to simulate how tourism demand might actually fluctuate. The function accepts parameters such as the start and end dates, a list of cities, and a seed for reproducibility. Inside the function, we first establish a date range that covers our desired period in monthly increments. We also prepare to hold our data for each city in a comprehensive list. For each city, the code generates demand data based on several key factors. First, we establish a base number of visitors per month, which varies by city, combined with a growth rate to model increasing demand over time. Seasonality is cleverly incorporated, using sign functions that reflect annual and semi-annual trends, replicating the typical peaks and valleys in tourism patterns. Additionally, we introduce two shocks, simulating real-world events that might disrupt or enhance tourism, such as festivals or economic changes. To add realism, we also include some noise, ensuring that our dataset reflects the unpredictable nature of tourism. The final demand is calculated through the interplay of these factors, producing values that are never negative, since that wouldn't make sense in this context. The resulting data frame consolidates all of this information, including dates, city names, and the generated demand, into a format that is easy to analyze. Once our data is generated, we display the first few rows, allowing us to verify that our synthetic dataset accurately reflects the expected structure and variability. As we move to the next cell, it's likely we'll explore statistical models or machine learning techniques to analyze this data for trends, ultimately aiming to predict future tourism demand. Cell 4. In this cell, we're setting the stage for a more comprehensive analysis by importing necessary libraries and defining essential functions to evaluate the performance of our predictive models. This is crucial because understanding the accuracy and reliability of our forecasts helps inform decision-making processes as we move forward. We start by bringing in powerful tools like NumPy and Pandas, which are fundamental for numerical operations and data manipulation. Then, we import specific metrics from the scalearn library, such as mean absolute error and mean squared error, which are vital for quantifying the difference between actual and predicted values. Additionally, we include model classes from SARIMA, Profit, and XGBoost, which allows us to apply various forecasting techniques later in our analysis. Next, we define the root mean squared error function, which computes how far off our predictions are from the actual outcomes. This metric is particularly important as it provides a standard for evaluating the accuracy of continuous outcomes. Alongside this, we create a function for calculating mean absolute percentage error, or MAPE. This metric helps us gauge the accuracy in percentage terms, making it easier to interpret and compare results across different datasets. An important detail to note is the use of a small epsilon value to prevent division by zero when calculating MAPE. This consideration ensures that our function remains robust, and we minimize potential pitfalls that could distort our calculations. Now that we've established these key metrics and prepared the groundwork for our forecasting models, we are poised to delve deeper into applying these concepts in subsequent cells. There, we will likely see how these metrics can offer comparative insights into the performance of various forecasting methods, further enriching our analysis. Cell 5. In this cell, we're diving into feature engineering, specifically tailored for an XGBoost model. This process is crucial because the features we create can significantly impact the model's performance by providing it with more relevant and informative data. The function defined here is designed to enhance our dataset by adding various time-related features. To start, we're creating a copy of the input data frame, which ensures that the original data remains intact as we manipulate it. The first two additions are the month and year extracted from the date column. These time features help the model understand seasonal trends and changes over time. Next, we introduce lag features, which are vital for time series analysis. By shifting the demand values by 1, 2, 3, 6, and 12 periods, we give the model the ability to learn from past observations, capturing trends over different lengths of time. This can be crucial, especially in applications where demand exhibits seasonal behavior. Additionally, we calculate rolling statistics. The rolling mean and standard deviation for the previous 3 and 6 periods can provide insights into the demand's stability and variability over time. These features allow the model to consider not just the current demand, but also how it has fluctuated in recent history. We also compute sine and cosine transformations of the month, which are helpful in modeling seasonal cycles. By encoding months in this way, we allow the model to recognize patterns associated with specific times of year more smoothly than if we simply used categorical variables. As you think about implementing these features, it's important to keep in mind the assumptions regarding your data. For instance, ensure there are no missing values, as lag and rolling calculations can break if they encounter nans. Looking ahead, the next cell will likely leverage these new features within an actual modeling context, possibly setting up an XGBoost regression to predict demand based on the enriched dataset we've just created. This should give us broader insights into how these features impact our predictive capabilities. Cell 6. In this cell, we're focusing on training and evaluating several forecasting models for demand data related to a specific city. This step is crucial because correctly predicting demand can significantly impact resource allocation and planning strategies. By splitting the dataset into training and testing samples, we can assess how well our models forecast demand based on historical data. The initial steps involve preparing the data by ensuring the date format is correct and that we have enough historical points. Over 24 is necessary to avoid issues. This guarantees that our forecasting will have enough information to base predictions on. Following this, we divide the data into training and testing sets based on a designated number of months reserved for testing. Next, the seasonal naive model is created by predicting future values based on the same month from the previous year, providing a baseline prediction. We then fit a SARIMA model to capture any underlying trends and seasonal patterns, using the training data to learn the relationships in demand over time. Furthermore, we employ the profit model, which allows for flexibility in handling seasonal variations and holiday effects by treating the training data in a specific format. For more complex relationships, we use XGBoost, which entails generating additional time-based features to enhance our model's predictive power. After all models make their predictions, we compile these into a single evaluation data frame, merging actual demand with predicted values for comparison. The debug section is particularly helpful in tracking the performance of each model throughout the evaluation, revealing any potential gaps or issues in predictions. An important decision follows. If any model lacks sufficient overlap in predictions with actual values, we implement a strategy to drop the least effective models to ensure the ensemble combines only reliable forecasts. Finally, we perform an ensemble of the remaining models, assigning weights based on their respective performance scores to enhance overall prediction accuracy. The results are stored and prepared for eventual assessment, with metrics like MAE, RMSE, and MAPE calculated to quantify each model's effectiveness. As we move forward, the next cell will likely continue building on these results, perhaps by visualizing the evaluation scores or further refining the forecasting process to enhance demand predictions across cities. Cell 7. In this code cell, we are executing a comparison analysis across different cities using a predefined dataset. The primary goal is to fit and predict models for each city, allowing us to understand variations in performance metrics and ensemble weights that summarize the results. The process begins by initializing an empty dictionary to store the results for each city. Next, we iterate through the unique cities found in the dataset. For each city, a filtered version of the dataset is created, which includes only the relevant data points. This is where we focus on each city's specific trends and characteristics. The filtered data is then passed into a function called fit-predict-city-models, which is central to our workflow. This function not only fits the models to the data, but also handles predictive analysis over a specified test period, in this case, 18 months. By setting the debug flag to true, we can gain insights into the fitting process, while allowing the model to drop those that don't perform well, ensures that our analysis remains robust and focused on the most effective models. After running the models for all cities, we print out the results in a structured manner. Each city's results are separated by a visual delimiter, making it easier to read the output. For every city, we display key performance scores and the ensemble weights. These weights are particularly insightful, as they indicate the contribution of each model to the final predictions, allowing us to gauge which models are most reliable for each city. As learners examine these outputs, it's important to recognize the potential impact of data quality and model selection on the results. Any discrepancies might lead to misleading conclusions, so careful consideration of the assumptions behind the model fitting is essential. Looking ahead, the next cell will likely take these results further, perhaps by visualizing them or delving into a comparative analysis that could reveal overarching trends and deeper insights. This step will be crucial for drawing meaningful conclusions from the data we've aggregated thus far. Cell 8. In this cell, we're delving into some crucial performance metrics that help us evaluate how our forecasting models are performing in predicting visitor demand. This is essential because understanding the effectiveness of different models can guide our model selection and refinement, ultimately leading to better predictions. We look at three specific metrics: the mean absolute error, or MAE, which measures the average magnitude of errors in our predictions; the root mean squared error, or RMSE, which penalizes larger errors more heavily; and the mean absolute percentage error, MAPE, which provides insight into the average percent deviation of our predictions. As we're analyzing the results for various cities, we find that the ensemble model generally outperforms individual models across all metrics for New York City, indicating that combining the strengths of multiple models leads to better overall accuracy. In this scenario, XGBoost stands out as the strongest single model. This suggests that it not only performs well on its own, but also lays a robust foundation for enhancing the ensemble's performance. For cities like London, Paris, Tokyo, and Dubai, we observe that Profit emerges as the best model in terms of RMSE. This highlights the importance of selecting the right model based on the specific characteristics of the data being analyzed, as different models may excel under different conditions. While the ensemble model consistently offers strong forecasts, it usually ranks as the second best option. This underlines a key insight: our weighting scheme, while valuable, does not always flawlessly aggregate model performance. One crucial aspect to consider is why the ensemble is not always the best choice. The inverse RMSE weighting provides a reasonable approach, but isn't infallible. To improve upon this, we can make use of validation windows to learn weights instead of relying solely on the test set, which can enhance accuracy. Another effective strategy involves constraining those weights, perhaps by excluding weaker models from the combination or employing ridge regression techniques to optimize the weights. Looking ahead, we can explore how these improvements to weighting and model selection can lead to even more refined predictions in our next analysis. Cell 9. In this cell, we're visualizing the tourism demand forecast for a specific city, which is crucial for understanding how future trends compare with actual past data. By plotting both actual demand and various forecast models, we gain valuable insights into expected tourism behavior, allowing for informed decision-making. The function we're using, plot forecast, accepts several parameters, such as the city's data, a title for the plot, a dictionary of the predicted values, and specific dimensions for the figure. Initially, a new figure is created using Plotly's graphing capabilities. We begin by plotting the actual tourism demand as a line on the graph, indicating past performance. This serves as our baseline reference. Next, the function iterates through each forecast model contained in the predictions dictionary. For each model, it adds another line to our plot, allowing us to visually compare the predictions against the actual demand. An essential feature in our visualization is the vertical line representing the split date. This is a pivotal moment where we separate historical data from our forecasted values, easing the interpretation of how well the models perform post this point. The layout of the figure is enhanced by specifying axis titles and customizing the dimensions to ensure clarity. After executing this function, we display the last few entries of the city's data frame to give a snapshot of the actual demand figures, ensuring we're grounded in real numbers. In the context of our analysis, we see that the tourism demand for this particular city follows a sinusoidal pattern without any phase shift or year-to-year variation, showcasing a consistent peak around March and a trough in November. This inherent cyclicality can help stakeholders plan effectively for seasonal fluctuations, though it's essential to remain cautious of external factors that might affect these patterns. As we transition to the next cell, we'll likely explore further details or additional visual comparisons, possibly delving into how well these forecasts are performing over time and what adjustments might be made to optimize predictions. Cell 10. In this cell, we're focused on filtering and preparing data for a specific city, NYC, to analyze and compare demand predictions from various models. This step is crucial because it allows us to visualize how well different forecasting methods perform in an actual scenario. The process begins with isolating the data related to NYC from the main data frame, ensuring we only focus on relevant entries. We sort this data by date, which is vital for any time series analysis since it allows for chronological comparisons. The filtered data is then stored in a new variable, making it easier to work with this subset. Next, we extract the predictions from the results for NYC, which have been generated by multiple models, including seasonal naive, profit, XGBoost, and an ensemble approach. This variety is essential because it enables us to see how each forecasting technique stacks up against one another. To prepare the output for display, we set the index to the date and rename the column for demand to improve readability. Each model's predictions is then added as a new column. Here, it's important to remember that because some of these models rely on historical data to make their forecasts, the first few rows of predictions may be missing. This is a typical characteristic of time series forecasting, where lagged features come into play, and while it's not an error, it's something to be aware of when interpreting the results. Finally, we reset the index to make the table look clean and presentable. The display command shows the last 25 entries, giving us a snapshot of how the models are forecasting demand over time. As we move to the next cell, we are likely to delve deeper into evaluating the performance of these models, discussing metrics that quantify their accuracy, and perhaps visualizing the results to better understand their effectiveness. This will set a solid foundation for comparing model performance and guiding future predictions. Cell 11. In this cell, we're enhancing the presentation of our data, specifically focusing on how numerical values are displayed. This step is significant because clear formatting makes it easier for us to interpret the information, particularly when we're dealing with large numbers that might otherwise be difficult to read at a glance. We're setting a specific formatting style for floating point numbers using pandas options to ensure that any decimals are rounded off and presented in a more digestible format, which will display values in a comma-separated fashion. By applying this formatting, we hope to clarify our data presentation and make it more user-friendly, especially when we're about to analyze or share our findings. In addition, we're leveraging the display function to show the last 25 entries of our dataset. This allows us to focus on recent or relevant data while ensuring that the updated formatting is visible. It's important to note that while formatting enhances readability, one should be cautious not to lose sight of the underlying data context or any critical details hidden by rounding. As we move forward, the next cell will likely build on this improved presentation, perhaps diving deeper into the analysis of the data we've neatly formatted. We may explore trends or insights that emerge from this clearer representation, so it's crucial to keep our formatted data fresh in our minds as we progress. Cell 12. In this cell, we're focusing on how to adapt our analysis for real tourism data, which is crucial for making our findings relevant and actionable. Understanding the structure of your dataset is key, as it shapes how we will approach our analysis. The suggested format for the data is straightforward. It should include the date, the city, and a measure of demand. Demand can encompass various metrics, each offering unique insights into tourism trends. For example, airport passenger arrivals can provide a snapshot of overall travel trends to a region. Alternatively, hotel occupancy counts can shed light on how well local hospitality businesses are performing. Visitor arrival figures, which are often collected by tourism boards, can help assess the popularity of a destination over time. We also have attraction ticket sales, which indicate how attractions are performing economically and how many visitors they draw. Lastly, short-term rental bookings reflect changing patterns in tourism, especially with the rise of platforms like Airbnb. The key here is to ensure that any data we collect adheres to this format, as it will facilitate easier analysis later on. However, it's important to remember that not all data types are equally useful. They should relate directly back to the demands of your analysis. For instance, if you seek to understand seasonal trends, you'll want data that captures variations over time. As we move forward into the next cell, we'll begin to explore how we can visualize this data effectively, transforming our structured input into impactful insights. This transition from raw data to visualization will be pivotal in understanding the narrative behind the numbers. Cell 13. In this cell, we dive into the vital reasons behind analyzing tourism demand using multi-model forecasting. The essence of this approach lies in its ability to provide cities with insights that directly influence operational and financial decisions. For instance, cities face significant decisions regarding airline routes, hotel staffing, and transit planning before demand materializes. Accurately predicting tourism trends can lead to substantial savings, enhanced revenue, and reduced risks, making precise forecasts a necessity rather than a luxury. The complexity of tourism demand demands a multifaceted approach. Different forecasting models, like Profit, XGBoost, and SARIMA, each capture unique elements of this complexity. For example, while Profit excels at identifying smooth trends and seasonal patterns, XGBoost is adept at recognizing nonlinearities and lag effects. By leveraging an ensemble of models, we mitigate the risks associated with relying on a single forecasting method, just as diversifying investments in a financial portfolio reduces overall risk. Another critical factor is the inherent sensitivity of tourism demand to unexpected shocks. Events such as pandemics, geopolitical turmoil, and climate changes can drastically alter visitor patterns. A single model might lead to overreactions or inadequate responses. By utilizing multiple models, we can reveal discrepancies in predictions, enabling early detection of instabilities and offering a range of scenarios that inform city budgets and infrastructure investments. Moreover, the dynamics of tourism pricing are heavily influenced by demand forecasts. Insights gained from model discrepancies can dictate when to optimize prices or adjust minimum stay requirements for hotels and attractions. For instance, if one model predicts a steady increase in demand, while another signals an impending spike, it prompts a strategic pricing response that can maximize revenue early on. From a public policy perspective, understanding and forecasting tourism demand allows for better management of over-tourism and its associated challenges, such as housing shortages and environmental impacts. This foresight empowers policymakers to implement measures that can sustain tourism without overwhelming city resources. Lastly, the ability to conduct scenario analyses further enriches our forecasting abilities. With a robust multi-model framework, we can simulate various what-if scenarios, stress test forecasts under potential shocks, and evaluate marketing campaign effectiveness. This blend of classical time series methods and machine learning not only illuminates the intricacies of tourism demand forecasting, but also illustrates how data-driven decisions can be strategically aligned with long-term city planning. As we look forward to the next cell, we will likely explore how to implement these multi-model approaches practically, turning the theoretical foundations we've discussed into actionable strategies for effective tourism demand forecasting.
Cell 14. In this final cell, we're marking the completion of our Jupyter Notebook journey. This closing step is essential, as it signifies that all the preceding analysis and visualizations have been compiled into a cohesive whole, culminating in a comprehensive understanding of the project's objectives and findings. Essentially, this cell serves as a wrap-up, emphasizing the work we've accomplished together. It's important to reflect on the key insights that have been gathered throughout the notebook. We began by setting the stage with our dataset, then carefully manipulated and analyzed the data, followed by creating visual representations that helped illuminate our findings. Each of these components plays a vital role in creating a structured narrative around the subject matter. As we conclude, it's valuable to appreciate the connections made along the way. For instance, how the preliminary data cleaning set the foundation for our more sophisticated analyses later on, or how each visual element reinforced the points we wanted to make.
It's also a moment to consider any limitations encountered throughout the process, which can serve as valuable lessons for future projects. Looking ahead, as you move on to the next notebook or project, think about how the skills and processes learned here can be applied. Whether you aim to tackle new datasets, explore different analytical methods, or refine your visualization skills, this experience lays the groundwork for your continued growth in data science.